All right, today we're going on a journey, and it's a wild one. We're going to start with an AI concept that sounds like it's straight out of science fiction, and we're going to drill all the way down to the actual silicon chips that make it possible.
So let's kick things off with a pretty mind-blowing question. Can an AI automate the entire process of scientific discovery and maybe, one day, even win a Nobel Prize? It sounds totally out there, but this is the kind of grand ambition that's really pushing the boundaries of AI research right now.
And, this idea is captured perfectly by this quote from a company called Sakana AI. They're not just trying to build a new tool that helps scientists out. No, their goal is to automate the whole shebang. This is a massive shift in how we even think about discovery.
And get this isn't just some far-off idea on a whiteboard. Sakana's AI scientist is a real system, and it does everything. It brainstorms new ideas, it writes its own code to test them, it runs the experiments, it crunches the data, and it even writes, illustrates, and peer reviews its own scientific papers. It's the full end-to-end research pipeline in a box.
And this is the part that'll really blow your mind. The estimated cost for this thing to generate one complete novel scientific paper from scratch is about $15. Yeah, for the price of a decent lunch, you can get an automated research project. I mean, think about what that means for a second. Suddenly, cutting-edge research isn't just for labs with multi-million-dollar grants. This could literally democratize science and accelerate progress like nothing we've ever seen before.
Okay, but here's the catch. To make a dream like the AI scientist actually work, you need a staggering amount of computing power. An AI this big can't just run on your laptop. It needs a massive cluster. We're talking thousands of processors all working together in perfect harmony. And trying to coordinate all of that creates a monumental traffic jam of data.
So this massive coordination challenge, it has a name: collective communication. Basically, it's the digital backbone that lets all those thousands of processors stay in sync while they're working on one huge problem. You can think of it like a team huddle, but happening millions of times a second. And if that huddle is slow or clunky, the entire computation just grinds to a halt.
And this leads engineers to a massive dilemma, a real headache. On one hand, you have static networks. They're super fast, but they're also rigid. It's like having a perfect highway system built for only one type of car. Great for that car, but a total mess for anything else. On the other hand, you have dynamic networks. They're flexible, but every time the data pattern changes, you basically have to stop everything and rebuild the roads, which causes these crippling delays. So you're stuck choosing between being inefficient or being painfully slow.
So that's the million-dollar question, right? How in the world do you build a network that's both screaming fast and incredibly flexible, so you can have the best of both worlds?
Well, the answer is a really clever framework called SWOT. And instead of just stopping all the traffic to reconfigure the network, it hides the delay in plain sight. Here's how it works. First, it splits the data up unevenly. So imagine a huge chunk of data goes down path A, and a tiny piece goes down path B. While path A is still chugging along with its big transmission, path B finishes super quick. And in that spare time, it starts reconfiguring itself for the next job in the queue. It's like a relay race for data, where one runner is already getting set up while the other is still running. The delay just vanishes.
And the results? Oh, they are absolutely staggering. You can see it right here in this chart from the research. Compared to the old ways of doing things, SWOT just blows them out of the water. It can slash that communication time by almost 90%. It doesn't just solve the dilemma of speed versus flexibility, it completely smashes it.
Okay, so we've solved the massive traffic jam on the data superhighway. Awesome. But fixing one problem always reveals another one, doesn't it? A super fast network is pretty useless if the chips it's connected to can't keep up. And that takes us even deeper down the stack, to the most fundamental layer of it all, the processor itself.
Now, to really get this, we've got to take a quick trip back in time. For decades, the way to make a computer faster was simple. Just crank up its clock speed. More gigahertz meant more power. But then, around the mid-2000s, that race just came to a dead stop. So, why?
You can see it right here on this timeline. The industry hit something called the power wall. Basically, if you tried to increase the clock speed anymore, the chips would generate so much waste heat they'd practically melt. They basically became tiny little furnaces, and you just can't build a computer like that. The whole strategy had to change. So the entire strategy had to flip. And this analogy just nails it. We stopped trying to build a single, brilliant sprinter,
and instead started building a perfectly coordinated army of thousands of slower but much more energy-efficient marathon runners. This idea, parallelism, is the absolute bedrock of all modern supercomputing, and it's what makes today's AI even remotely possible.
All right, we've seen the big dream up top, we've seen the network solution in the middle, and we've seen the processor revolution at the bottom. So now let's put it all together. Let's build the full stack that takes an idea like the AI scientist from a wild dream to a working reality.
Layer 1. It all starts here, at the foundation, with the silicon itself. Modern chips aren't built for raw, blistering clock speed anymore. They're designed for massive parallelism, packed with tons of efficient little cores that are all meant to work together as a team.
Then you've got layer 2, the superhighway that connects all those cores. To get them all talking to each other, you need incredibly smart, flexible networks. That's where clever scheduling tech like SWAT comes in, creating this dynamic fabric that shuttles data around without causing those digital traffic jams.
And finally, layer 3, right at the top of the stack, the application. This is where we come full circle. These incredible, groundbreaking ideas like the AI scientist are only possible because they can stand on the shoulders of the two powerful layers right beneath them.
So what's the big takeaway from all this? What's the one thing you should remember? It's that progress in AI is not just about writing a smarter algorithm. It's a full-stack problem. For these huge leaps forward to happen, you need a symphony of innovation at every single level, from the software dream all the way down to the silicon reality. And that brings us to one last, really profound question. As we build these unbelievably powerful systems that can automate discovery itself, who's making sure they discover things that are actually good for us? The tech is moving at a breakneck speed, and figuring out how to steer it, well, that's the next great challenge for all of us.